with my good friend and colleague, David Schuster and his group, making matter out of light. So I think before we even get into, what we mean by that in the specific cases that I'll tell you about, I think it's worth it to take a step back and talk about, when I say making a material, what do I mean really by a material? What are the requirements for that? And these themes I hope you'll see will be woven in throughout the remainder of the talk. So I would say that a material is a collection of particles that interact with one another and thereby organize or order. So what I've got here is each of these blue dots is just some kind of a particle. It has a mass, meaning if you apply a force to it, it accelerates or decelerates. And it attracts each of the other particles when they're far apart, and it repels each of the other particles when they're close together. So if I run this model and I turn on just a little bit of friction, what you see is that over time, these particles form, they sort of self-organize into a crystalline structure. That's how they minimize their energy. And you can see phononic excitations, you can see defects, you can see all of this richness from these extremely simple constituents. So the three essential ingredients is individual particles, that is to say objects with some kind of a dispersion relation, non-trivial relationship between their momentum and their energy, okay? These particles need to have some kind of interactions between them. And then we need some way to suck entropy out of the system. In this case, it's friction, but you can imagine all kinds of other approaches. And so this is what we're going to try to realize in making materials out of photons. And the hope is that this will inform us a little bit about what it really means for something to be a material. Before I go any further, let me just make a distinction between a classical material and a quantum material. The idea is that each of these little dots is a particle, and the size of the dot here, this blurriness, tells you something about the quantum uncertainty and its position, just its 0 point uncertainty. So the idea is, as you make these particles less and less massive, their position uncertainty becomes larger and larger. And when that becomes comparable to the interparticle spacing, entanglement between the particles starts to become important for determining the material properties. So more broadly, the point is you should have two competing non-commuting energy scales in your problem. Okay, here it's interaction energy and kinetic energy, but it could be interaction with an external magnetic field and interaction with a neighboring spin, what have you. Okay. So let me characterize a quantum material in one more way for you. And let's talk about cross sections to do that. So we've all learned about cross sections as undergrads, presumably. The basic idea is if I want to know what the cross section is of this green particle, what I do is I send past it a bunch of red particles, okay? And I ask how big the hole is that it casts a shadow in this distribution of red particles. That is to say, how many does it scatter away? And that cross-sectional area describes the size of the particle, okay? Or the cross-section, if you will. So the point is now that the collision probability is given by the cross-sectional area of this particle, kind of divided by the cross-sectional area of the beam of particles going past your particle. Okay, so now we have a good opportunity to distinguish between classical physics, or excuse me, classical particles and classical waves. The idea is if the uncertainty in the position of the particle is smaller than its cross-section, you more or less have a classical particle. Think about a marble here. A marble has some quantum uncertainty in its position, but it's sort of nanoscopic or femtoscopic. And its cross-sectional area is given by the radius of the marble. Right? So that's essentially a classical particle. By contrast, you can think about something whose position uncertainty is much larger than its cross-sectional area. And in that case, you essentially have a classical wave. And it's in this intermediate region where the cross-section is comparable to the size, to the position uncertainty of the particle that you start to get quantum physics. Okay, so we've sort of set the stage here. And now we want to talk a little bit about how one might try to explore this physics with photons, okay?
Hey, Jonathan, I have one question regarding
yes, sure.
Regarding this entanglement that you mentioned in passing. So maybe we'll come back to it. But what I want to ask is that, is there a, in a many-body quantum system, do you think of entanglement through a single parameters, like a dimensionless parameter which you can tune, or is that reasonable to ask? Like in your control of all these things that you were mentioning, is there some combination of these parameters that will ensure that there will be certain entanglement in this many body state?
Yeah, this is a great question. I think, you know, it depends a little bit about the specifics of the system that you're talking about, right? And in fact, Bill Phillips has pointed out that this story is brushing things a little bit under the rug. About partial wave expansions, and once you have multiple partial waves, should you think about the radius of the interaction or the actual cross section? But I think the basic idea is those things sort of scale together. So yeah, you know, if you look at, say, a two-dimensional electron gas, forget about it even having a magnetic field. Right, you can there at zero temperature ask about what is the density of electrons, right? And just knowing the density of electrons is actually enough information to know whether you're going to get a Wigner crystal or a or some kind of a Fermi liquid.
Right.
With the idea being that really there's just a dimensionless parameter that compares the 0-point kinetic energy to the typical Coulomb energy, right? And there's some transition in that energy scale. Now, that phase diagram, I guess, can be complicated. And indeed, in our problems, there's usually also a dissipation energy scale, so it's not quite a one-parameter space. But I think in many of the idealized systems, it's exactly as you say, it's just a one-parameter family.
Right. Okay.
Yes? Okay, so we want to make photons behave like particles. And so to do that, the first question we kind of have to ask ourselves is, what does it mean for something to behave like a particle? Well, the dot on the left is an electron, a marble, it doesn't matter. And it's moving to the right, and I'm going to apply a force on it to the left. Well, what do we see? It slows down and then moves back to the left, right? That's what we expect to happen for a particle. What happens to a photon as I apply a force to it to the left as it's moving to the right? Well, its color changes. It doesn't slow down, right? Its color just changes. So that's very annoying, and that is not at all the behavior that we expect of a particle. And you can understand this pretty straightforwardly in the sense that what a force does is change the momentum of a particle, and the velocity is sort of the derivative of the energy with respect to the momentum. So if you have a photon that has a linear dispersion, as they do in vacuum, no matter what you do to the momentum of this photon, it essentially always has the same slope here. And so it doesn't really behave like a particle in the sense that we would expect it to. The idea then is to trap the light in some kind of a medium that changes its dispersion relation, such that there is some relationship that's non-trivial between the slope of the energy momentum curve and the momentum of the particle. And that essentially imbues the photons with mass. So this is the quantitative way of saying it. We'll have an intuitive story later. Yes?
Sorry, so I have a question from Jufeng. So Jufeng, go ahead and ask your question.
When you mention the force on a photon, exactly what kind of force are you talking about?
So you're asking, how are we applying a force to a photon, right? Exactly. So this is a great question. Again, I've sort of brushed this under the rug. In practice, What we usually do to apply forces to photons is hybridize them with matter and apply forces to the matter, right? You make some kind of polaritonic quasi-particle, right? But yeah, so that's usually what I mean by that.
So it's really a matter photon quasi-particle you're talking about. So not strictly a photon by itself, because there's no way you can actually apply a force on a free photon. What I mean is what I mean, right?
Well, again, I guess the question is, what does it mean to apply a force to it? You have to have it interact with something, right? And exchange momentum with that thing.
Right.
So in some sense, if you put your photon into a medium with a varying index of refraction, right, that would effectively kind of apply a force to it.
Now, my question is actually probably a little deeper. Maybe you don't have a straight answer right now. I've been actually thinking about what is a photon for quite some time. I kind of come to the conclusions that there's no need to talk about photon unless there's matter involved. What I mean is that if you're thinking about free traveling light, it's not really necessary to invoke the concept of photon unless it is interacting with a matter.
I think
is a fair statement.
I'd have to think about the implications of that, but yeah, I see what you're saying.
Right.
I mean, I would say it's important to me to talk about photons because it's the title of my talk.
Right.
But I
know it's a very
deep
point. Question. You can skip it and let's move on to
yeah.
Okay.
No, I take your point. You say maybe you don't even need to think about photons at all. There's some sort of mediator of
unless there's a matter involved, matter interaction.
So there is a follow-up question to that from Abdullah. He's asking, are the hybrid quasi-particles massless?
They end up being massive, but in fact, we can even make the photons massive by trapping them between mirrors, right? So we will talk in detail about the specifics. I'm just trying to set the stage here, right? So literally the point is, if you trap light in some kind of a material structure, you can change its dispersion, right? And that gives the photon effectively mass, in this sense that if you change its momentum, that's all I mean by applying a force, change its momentum, right? Its effective velocity changes, okay? So that's challenge number one. Challenge number two is that if I take two electrons and I send them at each other, when they get close, they collide and go off in different directions. But of course, we know Maxwell's equations are linear. So if I have a solution moving to the right and a solution moving to the left, the sum of those two is also a solution, right? So the photons essentially don't collide with each other. So again, the question is, how can we make the photons collide? And to answer that, we should start by asking, well, really, how do electrons collide? Well, electrons collide with one another by exchanging a virtual photon, at a fundamental level. And then you integrate out this virtual photon and you have some effective interaction between your electrons, like our previous question pointed out. So you might ask, can I have the same thing for photons? Have the photons exchange a virtual electron? Well, it turns out pretty much everything precludes this Feynman diagram, but you can draw a crazier one that was actually recently observed at a collider, where you have photons exchange virtual electron-positron pairs, and that has a non-zero cross-section, but it's very, very small. That is to say, if I send two optical photons, say 1 eV photons at each other, one of those photons presents a cross-section to the other photon of radius like 10 to the minus 28 microns. Okay, just extremely small. So the point is, if we want to be in a regime where the interactions between these photons are substantial, this is not going to give it to us. But the interesting point is, you can look at the factors that appear in this equation, and what you see is that part of the reason that this quantity is so small is that the electron-positron pair that we've created is much higher energy than the photons that we sent in, right? So if we could go through a sort of closer to resonant intermediate state, for example, by colliding with matter and creating some atomic excitation, you could vastly enhance this cross-section. So one of the things that I'll show you is that by coupling to Rydberg matter, and we'll talk about why Rydbergs in a little bit, we can increase this cross-section between two optical photons up to a cross-sectional area of like 100 microns squared. And in some sense, this is really the secret sauce for the for making the photons interact. And for much of the physics in general. And this 100 micron squared is important because that's on the order or slightly larger than the wavelength of the light. So it means that we can go to a classical regime for these photons where they really behave like hard marbles, or if we make the interactions just a little bit weaker, the interactions are sort of on the same order as the effective de Broglie wavelength of the photons. And this puts us deep in a quantum regime. Okay, so the final challenge is that I told you that my model had a little bit of friction in it between those little marbles, right? What happens if I take out the friction? Well, then the particles never order. This should probably remind you of graduate students at the pre-colloquium cookies. I don't know if you guys do pre-colloquium cookies, but it kind of looks like this at UChicago when we do it. The point is you need a little bit of friction to get the self-organization. And so the challenge is if you add friction to your system, friction is coupling you to some kind of a reservoir, right? And so doesn't that make my system classical if I'm coupled to a reservoir that's continuously measuring the state of the system? But yet we put our quantum materials in dilution refrigerators and there's a reservoir there. So how do I understand that kind of interplay? And so what we're gonna find is that either by assembling the thing sort of spectroscopically resolving the eigenstates or cooling some subset of the system, we can get around this issue that more cooling makes the thing less quantum. Okay, so we're now more or less ready to get into our experiments, but let me just point out that there is a whole field of people studying how particles order in the solid state. You know, they're called condensed matter physicists. Maybe you've heard of them. They think about electrons whose dispersion relation is changed by a lattice of ions. The effective masses of the electrons is changed by the ions. And the Coulomb interaction between the electrons gives rise to the entanglement that makes the states sort of rich and interesting. So the cold atom community has long been focused on replacing this ionic lattice with a lattice of interfering laser beams. And that will change the dispersion relation for these laser-cooled atoms. And some van der Waals interaction between the atoms gives rise to the ordering of the atoms and the exotic sort of entanglement in any-body physics there. So the story I'm going to tell you today is that we will trap optical photons in either arrays of microwave cavities or in a multimode optical cavity. And we will make them interact either through Josephson junctions or through Rydberg atoms. And then we're going to see what kind of science comes from that, okay? So we've got these two platforms. One is a continuum gas of optical photons in an optical cavity, and the other is a lattice gas of microwave photons in this array of Josephson junctions. The system on the left is research that just takes place in my group. The system on the right is a collaboration with my colleague Dave Schuster. And what I'd like you to try to take away from each of these, yes, we'll talk about some interesting many-body physics, but to me, perhaps the main takeaway message, if you aren't an expert in this stuff, is what are the tools that we're using to make our photons behave like particles? What are the tools that we're using to make the photons collide with one another? And what are the tools that we're using to assemble into sort of ordered few to many body states? Okay, and so I'm going to tell you two stories, time permitting. In each case, I think these are sort of the main three questions to think about. So it's time for the first intermission. I know we've gotten a fair number of questions already, but if there are more, now is a good moment.
Yeah, I have just one brief question.
Yeah.
On your being quantum while being in a diffuse dilution refrigerator. So I thought that one of the ways you make it, you view it as quantum is that if there is a gap between the ground state and an excited state and your temperature does not take you out of this sort of ground state and few excited state manifold. But if there is a gapless system and you are, it's like a gapless system, gapless many-body system can be viewed as almost like a classical system, right? In some sense.
So here's what I would say. This is where I'm here. One, you short-circuited the second theme of the talk, which is good. When we talk about the circuits, we do focus on dissipative stabilization of gap systems. Mm-hmm. But my sense is that there's also a paradigm where the further away you get from the reservoir, mm-hmm. the less frequently you become entangled with the reservoir, and that sort of gets traced out. So my sense has been, at least in terms of the dynamics of the system, and this is something we intend to explore soon, the distance, the physical distance, if you will, or at least the coupling distance between the subsystem and the reservoir actually really matters. Hmm. Right. And I don't know how to quantify that yet. That's one of the challenges we want to look at next.
Because this is like a recurring theme in when people's trying to study isolated quantum systems and how does an isolated quantum system thermalize and
yeah, and this eigenstate thermalization hypothesis and these sorts of things. I agree. So this is the thing. We, in some sense, are not trying to make totally isolated quantum systems. With the photons, one of the interesting things that hopefully, time permitting, we'll find is that they're wonderful systems for engineering non-Markovian reservoirs to suck entropy out, right? But when you do suck entropy out, you are sort of measuring the system anyway, and so there's some question of to what extent that perturbs things. But I think that's an important question because it's very connected to the way nature works.
So there is one question from Jufeng, and then we will move on. Jufeng, ask your question.
Can you actually define the size of a free photon, or you can only define in the context of a hybrid quasi-particle?
I wouldn't say I can define the size of a free photon, but I can trap a photon in a cavity and tell you how big it is.
Okay, thanks. Got it.
Yeah, unfortunately, being an experimentalist, I have good ways to dodge these deep philosophical questions by having quantization boxes that exist in my lab. So I mean, I think these are really important, interesting questions, but our experiments do manage to get around the kind of stuff that now, it might be fun to think about how to not get around that stuff as well. But I think for here, we've got good tricks to get around it. So let's talk about optical photons. How do we make optical photons behave as particles? How do we make them interact? How do we study fractional quantum? All of it here. So the important story that I want to tell you is that photons in a multimode optical cavity behave as massive particles in a harmonic trap. So how should you think about this physics? Well, this is physics initially that was studied by people like Hui Deng and Yoshi Yamamoto in exciton polariton experiments and Martin Weitz in photon BEC experiments, and that we've since sort of broadened for our studies. But let me just explain the idea to you. So what I'm showing here is two mirrors shown in blue. And my claim is that when I send light into this cavity away from the axis of the cavity, the light will bounce back and forth inside of the cavity like a massive particle in a harmonic trap. And I don't mean it bounces back and forth in this direction like a massive particle in a harmonic trap. I mean in the transverse direction, okay? So how should we think about that? Well, we can ray trace, and you can see that this ray bounces back and forth along the cavity axis really fast. And if the mirrors weren't curved, it would just keep going upward forever, right? But because they are curved, the tilt of this ray changes over bounces, and it goes back and forth, up and down and up and down, okay? And so the picture you should now have in your mind is if I just look at this stroboscopic evolution in this middle plane, that's like a stroboscopic evolution of a massive particle in a harmonic trap, okay? And so the idea is that the tilt of this ray sort of tells you about the momentum in the vertical direction, how fast the photon is moving vertically, okay? And that can have any velocity that you want just by varying that tilt, okay? And then the tilt converts into a displacement based on the length of the cavity. The longer the cavity is, the more displacement you get per round trip. And so that tells you the relationship between the momentum and the velocity. It sort of determines the effective mass of the photon, if you will, okay? And then the point is the curvature of the mirrors changes the tilt, right? And that effectively acts like a trapping potential. So we can be a little bit more formal about this. The point is, if I have a massive particle in a harmonic trap, we know that the eigenstates are Hermite-Gauss in space and uniformly spaced in energy. This is just a quantum harmonic oscillator. But of course, if I make a two-mirror optical cavity, you can ask, what are the modes of that cavity? Well, they are Hermite-Gauss in space and they're uniformly spaced in energy, okay? And so what that means is, if I send light into my cavity displaced upwards a little bit, here I've shown it as displaced to the right from the cavity axis a little bit, I can write that as a superposition of the lowest mode of the cavity, which is this single blob, and the first excited mode, which is two blobs like this, one above the other, cavity mirrors this way. And the point is those have slightly different frequencies. And so half a different cycle later, this plus sign has become a minus sign, and now my photon is displaced to the left of the cavity axis. So this is exactly the same story as if I have a massive particle in a harmonic trap and I displace it from equilibrium a little bit, I can write its wave function as a superposition of the eigenstates of the harmonic oscillator. So this is just to say that because the modes of this cavity are these Hermite-Gauss modes, the mapping is basically perfect. Okay, and you can understand it in terms of the ray tracing if you prefer, but this math really makes it sort of quantitatively true. Okay, so the picture you should have in your mind, this is an artist rendition where I'm the artist. I've drawn two cavity mirrors here, and the light is bouncing back and forth vertically. So we picked a single longitudinal mode of this cavity, and then I ask, how fast does the light oscillate back and forth horizontally? And that horizontal motion is this harmonic trapping that we were talking about. Okay, and so that's the basic physics that we want to go with. So the point was, we understood that the free propagation of the photon along the cavity axis kind of gave rise to this mass. The mirror curvature gave us a trap. But then you might say, well, the last interesting quadratic term is a mixture of a mass term and a trapping term, or excuse me, a position term and a momentum term, right? XPY minus YPX should give us a magnetic field. Maybe there's a way to make that just by manipulating the shape of our cavity. And so it turns out by twisting the cavity out of the plane, you can make the photons behave as though they are massive particles in a harmonic trap in a magnetic field. So how does that work? Well, first, let's talk briefly about periscopes. So I'm going to look at a tree in this periscope, okay? And what you see is that if I look at a tree at the top, if it's vertical at the top, it's vertical at the bottom. But what if the two mirrors of the periscope are rotated by 90 degrees with respect to one another? Well, now I have a vertical tree at the top and a horizontal tree at the bottom, okay? And so the picture you should have in your mind is that as you rotate the top mirror with respect to the bottom mirror, the image of the tree gets rotated. And so if I could take these two mirrors and then add two more to close this into a closed loop, on each round trip through the cavity, the image gets rotated a little bit. I'm not talking about the polarization, and that gets rotated too, but we're going to ignore that. The actual ray trajectory, or the image, whichever way you want to think about it, literally gets rotated. So the idea is to make a 4-mirror cavity and twist it out of the plane, okay? And the idea now is that on each round trip through this cavity, the ray trajectory gets rotated a little bit around the cavity axis. That turns the lab frame into a rotating frame. And so for those of you who are Russian, you learned in elementary school that you can model a rotating frame as providing two fictitious forces. The rest of us learned this in college or graduate school. One of these fictitious forces is a centrifugal force, right? And the other one is a Coriolis force. The Coriolis force looks like omega cross P, which is just some vector cross mv, right? So I can write it as v cross b. And the centrifugal force is a force radially outwards, which is just the opposite of a harmonic trap. So I can cancel this centrifugal force with a harmonic trap, and then all I'll be left with is this Coriolis force. And this Coriolis force is exactly the same as a Lorentz force. So the idea that, pardon, yes.
How do I track this back and forth bouncing in this 4 mirrors? So you had this transverse motion, which is like a harmonic trap, right? So how do I track that in this 4 mirror configuration?
What do you mean? You mean experimentally?
Yeah, so while you are rotating this, you are kind of...
no, you fix it. You don't have to rotate it continuously. You pick a fixed angle.
Okay.
Right? And the point is, even at a fixed angle, this periscope effect gives you a rotation on each round trip.
I see. So that fixed angle is related to this omega.
Yes, exactly. Right. And so if you want, the correct way to do this is to kind of generate a Christoffel connection for the fiber bundle as you go around. Right. And this is sort of what we do, except it's a little simpler than that, because the group transformations are 4x4 matrices. Mm-hmm. It's essentially ray optics, but in one higher dimension than people usually use. And it just all comes right out. So we can talk mathematically about how to do it later if you'd like. But it works. It's just a little bit of geometry. Okay. So the idea is, if I make a 4 mirror cavity like this, I've made a 2-dimensional harmonic trap for the photons. And then you can think of the modes of this trap. This is the lowest mode of that 2D harmonic oscillator. I can have an excited mode along X, an excited mode along Y, 2 excitations along X, 2 along Y, 1 along X, 1 along, and so on and so forth, right? Okay. The point is, now if I twist this cavity out of the plane, these Hermite-Gauss modes can no longer possibly be eigenmodes of the cavity, right? Because on each round trip through the cavity, the image gets rotated a little bit. And to be an eigenmode, you have to come back to yourself up to a multiplicative constant under a round trip, right? And so the point is, these can't be eigenmodes. It'll be superpositions of these that are eigenmodes. In fact, it'll be this one plus or minus I times that one. It'll be a ring, okay? And the ring whose phase winding goes in the same direction as the twist of the cavity will go down in energy. And the one whose phase winding goes the other way will go up in energy. So we do these numerics, and sure enough, what you see is that you can make these rings all degenerate in energy, okay? And this family of degenerate ring modes has a name. It's called the lowest-Landau-level, right? And this is the point where the twist creates a centrifugal anti-confining force, which precisely canceled the harmonic trapping from the mirror curvature, right? And then you've got your lowest-Landau level, and you can make the photons interact with each other on top of that to do interesting physics. Mm-hmm. So we take super polished mirrors, we stuff them into a 3D printed structure. We see these beautiful ring modes. We can then do spectroscopy on this system as a function of the length of the cavity. It's a few centimeters long. And as you tune to this degeneracy point, you can zoom in and see that we have an avoided crossing of only like a megahertz or two as we bring all of these modes into resonance with one another. So that's saying that kind of the typical disorder in our Landau level of photonic states is of order a megahertz or two.
Yeah,
okay?
So Vinod has one question. So Vinod, go ahead.
Yeah. So John, in your measurements, you fix the angle. So nothing is rotating in one set of measurements. And then do you rotate one of the mirrors to another angle and then do another set of measurements? Or is everything done at the same set, in the same optical setup?
You're saying to see this avoided crossing?
Yes, yes, yes.
So what you can see is we very slightly changed the spacing between the mirrors.
Ah, okay.
And the point is that changing the spacing, I told you this very simple story that the trapping frequency is determined just by the mirror curvature. But in fact, it's kind of a Floquet system, right? You get some free propagation, then you get some mirror curvature, then you get some twist, then you get some more free propagation, then you get some more. So you have all of the terms are intermixed a little bit.
Okay.
And you can just change the length of the cavity to effectively change the harmonic trapping frequency.
Okay.
Okay.
Thanks. Yeah.
You're welcome. So anyway, we get this non-degeneracy of a couple of megahertz. And as long as we have interactions between our photons that are larger than that, we should be able to explore fractional quantum Hall physics of the photons. So what I'd like to do is skip some of these stories about how we put the photons on a cone, how we measure the Chern number, and just talk a little bit about how we make these photons interact with each other. Okay, so the basic idea that you should think about is I'm going to send this light through a cloud of atoms. And the idea is the light that we're going to send through is at 780 nanometers. It's these bottom photons here. And as the first photon enters this cloud of atoms, it slows down. Why does it slow down? Well, one way to think about this is kind of like the index of refraction of the atoms. Basically, the point is the photons get absorbed by the atoms. And indeed, we've created a situation where when a photon comes in, it gets absorbed by one of the atoms, taken up to a 5p state, which is a low-lying excited state. And then we take that 5p state and we use a laser to take it up to a very high Rydberg state, okay? And this high Rydberg state can be very, very long-lived, which means that the photon goes through the medium very slowly, because most of the time it isn't a photon, it's an atomic excitation, okay? So the light enters the medium and then slows way down, because mostly it's just an atomic excitation that's then re-emitted and then moves forward a little more and gets reabsorbed and moves forward a little more, on and on and on, okay? So the interesting question is, what happens when a second photon enters the medium? Well, the point is, if this second photon is far away from the first photon, it sees this same level structure that I drew on the right. But if it gets near the first photon in space, well, these Rydberg electrons are in orbitals that are gigantic, okay? We've chosen like the 110 or n equals 110 orbital, which has an orbital radius of like a micron or two, okay? And so what that means is if the second photon tries to excite an atom that's within even say 10 microns of the first photon, what it will see is that this Rydberg level has moved away. And so the atoms can no longer absorb the photon and go up to this Rydberg state. And so what that means is if the second photon gets near the first photon, it actually moves fast instead of slow, okay? And so what you have is that the second photon sees an index of refraction that varies with position based upon your distance away from this photon. Photons, which is the regime of classical nonlinear optics, but between a single pair of photons, which is the regime of quantum nonlinear optics. Okay, so we're now in a position to see this experimentally. So we put this inside of a cavity. The picture you should now have in your mind is that the harmonic trapping comes from these cavity mirrors. Okay, the photon moves back and forth from left to right, but it drags with it a collective excitation of the atomic gas, such that if a second photon comes in, they can collide with each other using these atoms that we've put in the cavity. Okay, so how does this?
One question. So Gustavo, go ahead.
Go ahead. Yeah.
So is it possible to have an attractive interaction, or can you only make repulsive interactions between photons?
Super cool question. The question really is, in practice, does the index of refraction go up or down when the other photon gets near? And so it turns out by playing with detunings from these atomic lines, you can get either one. And in fact, the other thing that's interesting is that by changing the length of your cavity, you can even make the mass of the photon negative, right? And so what that means is that if you apply a force to the right, to the left, the photon accelerates to the right, right? So either of those two tricks can be used to change the interaction from attractive to repulsive, right? And so I hope that this is sort of starting to give you a flavor of what makes this kind of an approach so exotic and different from trying to study this kind of science with cold atoms or electrons. The advantage of studying condensed matter physics with electrons is that electrons give you these behaviors naturally, right? That's what inspired us to write down these equations, right? Cold atoms, the physics comes out still pretty naturally. With photons, you have to work a little harder. You have to trap them in something. You have to add atoms to mediate interactions between them. But then at the end of the day, boy, do you have a lot of flexibility in the models that you can realize, right? Because, so that's the curse and the blessing.
Yeah, because an attractive interaction should change completely, right? How your levels will be. And you basically don't get a fractional quantum Hall effect emulator. You should get something like closer to a condensate state, right?
So this is an interesting question. We'll come back to it a little bit more later. And in fact, it may be that I don't think I'm going to get time to talk about the circuits, but if you stick around, we can chat about them. The basic point is that because these systems don't really naturally have anywhere to dissipate excess energy, attractive and repulsive interactions in some ways behave the same way, right? The point being that you stay in some kind of a constant energy state, right, for the whole system. And so you can't shed the excess energy that would be required to give you a condensate, right? So you ask, what is the ground state at fixed particle number? What is the eigenstate at this particular energy? Tends to be the question that we ask. And so you can sometimes get the same physics for repulsive as for attractive interactions.
So there is a Vinod, go ahead.
Yeah, so just to clarify, are we realizing polaritons with the Rydberg states here, or are we, okay, so they are hybridizing. You're going into the strong coupling regime.
Yes, so these are, so these would be called Rydberg polaritons.
Okay.
So the first set of experiments I'll show you, we do this in a single mode regime. So the idea is we take a cloud of atoms, we laser cool it, we transport these atoms in an optical conveyor belt into our optical resonator, and then you can look at the cloud of atoms. The cavity mode is like 20 microns across, the cloud of atoms is like 100 microns across. We then slice the cloud of atoms down until it's very, very thin, so that effectively it provides 2D physics within the atomic cloud. And then we can start to probe this and explore the quasi-particles of the light in the matter. And what we're going to find is that they are very, very strongly interacting, okay? Now, you might ask, why do we have to do this in a vacuum chamber? The basic answer is that these Rydberg atoms are extremely delicate. If you have electrons with an orbital radius of like 2 microns, man, any air particle, anything will just tear those electrons off. So you really have to be under high vacuum for this kind of science to work. Okay, so the idea is if you just perform spectroscopy on this system, you can see these 2 little bumps on the sides. Those are what people typically call vacuum Rabi peaks from 2-level physics. We're not so interested in those. That's why we haven't zoomed in. We have this nice, tall, really narrow peak in the middle, though. This is when a photon enters the cavity and becomes a Rydberg polariton, okay? That's a quasi-particle which is part optical photon and part Rydberg excitation, where the strong interactions come from the Rydbergs, okay? So this cavity is, 6 centimeters long, but what we expect to see is that these Rydberg polaritons should be so strongly interacting that I can only put one of them into the cavity at a time. If I shine a laser on the cavity, once one polariton goes in, the next one reflects off, and then we can't get another one in until the first one leaves. So the first signature of this is this kind of blockade physics. You can think of this as like looking at an electronic quantum dot, but you could actually look at the individual electrons transiting through the dot. And so what we see is that conditioned on having just detected a photon leak out of the cavity, over the next 10 or 20 microseconds, the probability of having another photon leak out of the cavity is very strongly suppressed, because the system could never have two polaritons in the cavity at the same time. Okay, so this is if we only have a single mode accessible to these polaritons. We engineer these very, very strong polariton blockade interactions. So the next thing we want to do is combine this twisted cavity with these strong interactions to try to explore topological physics. So let me just tell you what the protocol is qualitatively for doing that, and then we'll talk about how it works in practice. So the typical paradigm of cavity quantum electrodynamics is you take a cavity with a single mode, you put one atom in it or whatever, and then you say, well, if I try to send one photon in, it can go right through the cavity. We're looking at the lowest mode of the cavity. But if I try to send a second photon in, there's some energy cost due to the atom-mediated interactions between these photons to putting in two photons. So I can only put one in at a time. This is Jeff Kimball's classic photon blockade experiment that's been repeated in a number of different platforms. And that's sort of what I just showed you for our Rydberg polaritons. Now, the thing that I want to convince you is sort of interesting and different is, what if we allow the photons to live in multiple modes of this cavity? How do they self-organize to try to more efficiently go through the cavity? So let's say I send photons in this ring mode, which I've designated L equals 1 unit of angular momentum. Well, the idea is, as before, I can send one photon in, no problem. But if I try to send two in, your intuition might be, well, these photons are still repelling each other through this Rydberg-Rydberg interaction. So I shouldn't be able to put two photons into this mode either. But the point is that, in fact, two photons in the L equals 1 mode is not an eigenstate of the interaction potential. These two L equals 1 photons can collide and conserve both energy and angular momentum by becoming one photon with 0 units of angular momentum and one photon with 2 units of angular momentum. So what I need to ask is there some superposition of two photons with 1 unit of angular momentum superposed with one photon with 0 units and one photon with 2 units that has no interaction energy, where the photons manage to avoid each other in space? And the answer is that Robert Laughlin got the Nobel Prize for figuring this out. And the answer is yes, there is such a state. So let me write it out for you. If Z1 is the location of one of the photons, and Z2 is the location of the other photon, where Z is a complex coordinate, I write it as X plus IY, like the real part of Z is the X coordinate, the imaginary part is the Y coordinate. The idea is that this wave function is a combination of these three lowest Landau-level wave functions that I wrote down, these three ring modes, and it keeps the photons apart from each other. How does it keep the photons apart? Well, when Z1 is equal to Z2, the wave function is 0. So the photons stay apart from each other. And in fact, now I can just expand out this product. And I see that I have Z1 squared, e to the minus magnitude of Z1 squared, times e to the minus magnitude of Z2 squared, which is one of the photons in this lowest mode and one of the photons in this big ring mode, okay? Z1, Z2, which is each of them in this intermediate mode, and Z2 squared times Z1 to the 0, which is the other one with 2 units of angular momentum, and the other one with 0 units, okay? And so the point is, it is exactly those three states that I told you about, and there's no interaction energy between the photons. So the point is, if you send two photons into this L equals 1 mode, what will come out of the other side of the cavity is a 2-photon Laughlin state, okay? And so we actually realize this experimentally. We generate photons with the right angular momentum using essentially a ripped apart data projector to generate the correct phase mass. We align those photons into this, we call it our twisted polariton collider, where the photons can interact in this twisted cavity through these Rydberg atoms. And then we measure the angular momenta of the photons that come out. And indeed, what we see is for a single mode, we get this blockade effect. And when we have access to multiple modes, the blockade is much weaker. That is to say, pairs of photons can come through the cavity, right? Due to this ability to transmit Laughlin states, okay?
So it seems that it's almost like a classical state, right? The way you have deconstructed it.
The Laughlin state is a classical state. In what sense?
Means you just have this photonics. There is no quantum source of light here. So you just kind of are, there is only interactions and classical light, right? In this experiment.
So what I would say is what's happening is we have non-trivial quantum dynamics inside of the cavity, right? That essentially distills out an entangled state of the photons from a classical input field, right? The point being, this entangled state is actually an equal superposition of 2 photons with 1 unit of angular momentum and 1 photon with 0 and 1 photon with 2, okay? And so, but I sent in 2 photons with 1 unit of angular momentum. Right. So what happens is 2 of these minus 1 of these and 1 of those gets transmitted. And 2 of these plus 1 of these and 1 of those gets reflected. So it's a filter that filters out particular entangled states into the transmitted and reflected ports.
So you just classically mimicked exclusion principle somehow, and then that's enough, it seems, right? To get a...
Well, this is the thing. The bosonic Laughlin state has a second power here, not a third power. Right. So this is not coming from the exclusion principle. It's coming from the strong interactions. Right. Okay. So the point is, this state with a minus sign is at 0 energy, and that other state with a plus sign is at a higher energy. And so the only one that gets transmitted is the one with the minus sign.
Okay, makes sense. Because I think it's a artifact of bosonic system, being a bosonic system.
Yes. So it really relies on the strong interactions and having a lowest Landau level. Because if you didn't have a lowest Landau level, you could conserve angular momentum by going to a whole bunch of other states of the optical field that would not produce a Laughlin state. Okay.
So there is one follow-up question from Joel. Joel, go ahead. Joel, have you unmuted yourself? So I cannot hear Joel, but let me read his question. What are the statistics of Rydberg polaritons? Bosons like to bunch, fermions like to avoid.
So the statistics are bosonic, right? That's why this is weird. These things avoid each other due to the interactions, not due to their statistics. It turns out the polaritons always get their statistics from the photons, no matter what the statistics of your atoms are. Okay, because the atoms aren't moving around in space. The photons are moving around in space. And that's a subtle other story. So the point is that experimentally, we can see that the pairs of photons make it through the cavity. And then we can actually measure the spatial structure and see that when we get 1 photon effectively with this higher angular momentum, we always get 1 of the lower angular momentum. So we send in 2 intermediate angular momenta, and they collide and go into the higher and lower angular momentum modes. And then we can also measure the phase of this superposition between the starting state that we sent in and this pair of scattered states by looking in space rather than in angular momentum, and seeing that the photons are anti-bunched in space as well.
So there is one question from Gustavo. Does the exponent changes for 3 photons?
So that's a great question. That's the next set of experiments that we intend to look at. You can reach both different exponents and the same exponent, but for more photons, right? So you can write down a 3-photon bosonic Laughlin state. We're looking at, say, nu equals 1/2 here, right? And then that would still be a second power, okay? But you could also make a 2-photon with a 4th power there, right? Which would be a nu equals 1/4 Laughlin state. And so building these bigger states requires a different set of tools, because this approach that I've shown you doesn't scale very well to bigger Laughlin states, but it's sort of the same kinds of ideas.
And what determines the exponent? I know in the Hall effect, what tells me what the exponent is. It's just like the ratio between number of particles and number of fluxes.
Yes. So this is a great question. Here, we've constrained it by angular momentum conservation, okay? The point is we injected particles with L equals 1. This system conserves angular momentum. So if you inject 2 particles with L equals 1, the only other accessible state is one with L equals 0 and one with L equals 2. So you've kind of constrained yourself to 2 units of angular momentum in your system, okay? The dissipative stabilization schemes, which again, after the talk, I can maybe share a little bit with you about how those work. It seems more promising to explore these different incompressible plateaus. But yeah, for this set of experiments, we constrain it through the preparation scheme. This is what I would call spectroscopically resolved preparation. Okay.
So one more question, sorry. So since we can have other exponents, for instance, if we constrain the angular momentum to be 3, this Laughlin wave function will fail to be the ground, not the ground state, but the state of my system, right? Because then
so let's talk about that a little bit more carefully. I mean, again, this is the really rich, interesting place that we're going to go next with these experiments, I think. Yeah. If you send in photons with 1 unit of angular momentum, right, you can put up to 2 in. And if you try to put a 3rd one in, there is no way that 3 photons with 3 units of angular momentum can avoid each other in the lowest Landau level. 3 units total, right? Right, so you will never succeed in putting the 3rd photon into your cavity.
Okay.
But now, imagine that I send photons in each with 2 units of angular momentum, okay? The point now is if I send a 2nd photon in with 2 units of angular momentum, there are 2 states that I can go to. I can either have 2 photons each with 2 units of angular momentum, or they can collide. Actually, it's more than 2. Well, let's be careful. Or they can collide, and when they collide, one of them can go to 1 unit of angular momentum, and the other one goes to 3 units of angular momentum, right? That has the same 4 total units. Or they can go to 0 units of angular momentum and 4 units of angular momentum, right?
Right.
So the question is, what is the structure of those states? Well, it turns out you can write it as either a 2-photon Laughlin state with 1 at nu equals 1/2 with 1 quasi-hole at the origin, right? Or like a nu equals 1/4 Laughlin state, right? And those two, at least in terms of contact interactions, are energetically degenerate.
I see.
Right? But which one is preferred will be determined by microscopics. Yes?
Okay.
But now, if you sent in a 3rd photon, now it has a strong preference, right? Because now we have 6 units of angular momentum and 3 particles. So the only 0 energy state is a nu equals 1/2 Laughlin state.
I see.
Does that sort of answer your question?
It does. Thank you.
So look, I don't want to keep everyone past the end here. This is just to say we can measure that they're anti-bunched in space as well. The final state that we've produced is actually, to be quite technical, a nu equals 1/2 Laughlin state on a cone for technical reasons with a quasi-hole at the origin. So this is where the second intermission would normally be. And then we would talk about circuits. But instead, I think I will just point out the people who really did the work. This is my group and also my collaborator, Dave Schuster. The photon experiments were conducted by the last generation of students and postdocs, primarily Nathan Shine, who's now a postdoc at Gilla and a DEMA thesis prize finalist, really a rock star. And Logan Clark, who's was my postdoc and is also just a really amazingly creative, terrific, incredible scientist. So with that, I'd like to thank them and all of you for hanging out for the last hour.
Yeah, thanks, Aaron.
And I will stick around if anyone actually wants to hear about circuit stuff afterwards. We can do that. But you guys had so many fun questions that we didn't even get to it.
So there were a couple of questions. Jufeng, you first, and Kevin next.
Oh, okay. This may be still a kind of theoretical, but it gets to the point. I think one of Shirin's earlier questions. A lot of things you've been talking about are still classical modes, right? The Hermitian Gaussian modes and within the mirror cavity. My question is, has someone actually properly quantized these cavity modes so that we can actually comfortably call them cavity photons?
So this is a very interesting question. I think you're asking at a more formal level than I typically worry about. For me, I guess the answer that I would give is if I take a mass on a spring, right? I can. Well, is that really the best way to do it? Yeah, I don't think we need to make it that complicated. I don't know. I mean, it's quantized at a level that I trust, right? But my guess is if you're worried about it at the level of like Elliott-Lieb and dealing with all of the possible divergences, my guess is that you probably would not be satisfied with the way it's been quantized.
Right, because like just sort of a background, me and one of our colleagues actually took like 2 years just to quantize a beam of Laguerre-Gaussian mode. It's actually highly non-trivial, even in the case of a free propagating case. I
would think free propagating would be harder to quantize than a box, right?
It is, well, it's the first place to start because if you couldn't even properly quantize in the free propagating case, then putting mirrors will it's a nightmare, kind of with the curvature and the stuff like that. And anyway, so I understand this is kind of beyond the level you kind of typically worry about in this experimental setup. But I'm just a little uncomfortable kind of interchanging the language between cavity modes and calling cavity photons directly.
So this is, I would love to understand afterwards actually what the challenges are. The way that I tend to think about all of these things, and maybe this is a naive experimentalist view, is once I know what the modes are of a system, the quantized excitations of that system live in those modes.
It is actually quite different. The kind of angular momentum you're talking about are classical angular momentum. whether you can actually translate into a quantum angular